Yes.
Okay, so we should start the session because we are getting late. Okay, assalamu alaikum everyone. I hope you are doing well, and I welcome to all of you once again for the lecture 4. And I hope the previous session has gone well with you. And today lecture will be about a single, dual, or multi-band antenna. Okay, so in this lecture we will study some research paper, and then I will give you some tasks to show me at tomorrow. Okay. Okay, so let's start with this paper. Okay, this is a dual band antenna. We will study only dual band antenna. Okay, and we will neglect other things, meta surface and off body devices. Okay, we will study in the relevant topics. Okay, but the main focus is dual band antenna. Okay. This is my first article. When I started my research, my first article was published in IEEE, and we will study about it. Okay, so let's start with this design. Okay. Okay, in order to read any research paper, you need to know the values and substrate material and the dimensions. Okay, for this material you need to study you will find one section in the research paper, in every research paper. Okay, in the design section, or you can say it will be a proposed methodology. Okay, so you need to read this paragraph one time. Okay, and you need to know what is happening here. Okay, you can see here it is using FR4 substrate. Okay, with the thickness of 1.6 millimeter. Okay, and what are the properties of the FR4 substrate? You can see here relative permittivity is 4.3 and the loss tangent is 0.025. Okay, and the size of the antenna is very small, that is 30 cross 14. Mean always remember, the first one is the length, the second one is the width, and the third one is the height. Okay, or thickness of the substrate. Okay, so it means you need to draw this one first. Okay, so we open the CST software, and also check the frequency range that they have used. Okay, from 1 gigahertz to 7 gigahertz. So you need to set the frequency range from 1 gigahertz to 7 gigahertz. Here you need to write 1 gigahertz to 7 gigahertz. Okay. Okay, now you can see here, your design is operating at two different frequencies. The first one is at 2.45 gigahertz and the other one is at 5.8 gigahertz. Okay, so the main focus is these bands. Okay, so you have to write here 2.45 gigahertz, 2.4, 2.45, 2.5 gigahertz. Okay, and the other one is 5.7 gigahertz, 5.8 gigahertz, 5.75 gigahertz. Okay, and 5.85 gigahertz. Okay, now click next, and you can write here dual band antenna. Okay, if you want to save this file. Okay, now click finish. Okay, so now let's start with the substrate first. You can see here in this design, the blue one is the substrate. Which substrate? FR4 substrate. Okay, so you need to make a substrate, use a substrate with these dimensions. Okay, and all the dimensions are in millimeter. Okay, so you need to choose the brick. Okay, and you can write here substrate and minus ws, width of the substrate by 2. Dear Aisha, please turn off your microphone. Okay, now length of the substrate, and that what is the thickness of the substrate. They are using 1.6 millimeter. Okay, so you need to click on the preview and you can see here what is the width of the substrate is 14 millimeter. Okay, so write 14 millimeter, and the length of the substrate is 30 millimeter. Okay, so you need to write here 30 millimeter. Okay, and the thickness of the substrate is here 1.6 millimeter. Okay, 1.6. Okay, now you need to choose the FR for substrate. Click on the load material from material library. Okay, and write here FR4. Okay, or you can write here FR4 lossy material. Okay, and click load and just click OK. Okay, so you can see here this is your FR4 substrate. Okay, the size is very compact. Okay, you need to, you can change the color so that it is more visible. Okay, now what the next step, just make sure either you have used the same dimensions or not. Okay, okay, you can, it is not visible here, but I don't know why. Okay, the length is 30 millimeter. Okay, 30 millimeter, yes, and width is 14 millimeter. Okay, and the thickness you can check here 1.6 millimeter. Okay, okay, now the next step, what is the next step to now the question arises, from where should we start? Okay, so you should always start from the field line. Okay, and the ground plane. Okay, so first you need to draw the ground plane. Okay, this is the CPW ground plane. This is the CPW ground plane. Okay, so you need to know the length and width of the this ground plane. Okay, so LG and WG are the length and width of the ground plane. So you need to move your WCS, align your WCS at the corner of this substrate. Okay, at this corner. Okay, so you need to write here this is the left CPW, so you can write here CPW left. Okay, CPWL. Okay, and in the U direction you have the width of the ground plane, and in the upward direction you have the length of the ground plane. Okay, and thickness of the copper is TP. Okay, and you need to choose the copper annealed. Okay, this one. Click on the preview. Okay, now it is asking for the width of the ground plane. So what is the width of the ground plane? WG. See the table. In every paper you will have a table. Okay, this is a table. So where is WG? This is WG, that is 6.35. okay, 6.35. okay, and the length of LG means this is the length of the ground. Okay, 2.5. okay, 2.5 here. Okay, and the thickness of the patch is 0.035. okay, so you have a copper here. Okay, now move your WCS, I mean align your WCS on the other corner. Okay, and click the brick again, and then this is the right CPW, so you can write here CPW or. Okay, so in the Umax you don't need any value in the Umax, you need in the opposite side, so you can write here minus in the U direction you have a WG, means width of the ground plane. Okay, so you can write here WG. Okay, and in the upward direction you have the length of the ground plane. Okay, you can see here, and TP, thickness of the patch. Okay, now click OK. So you can see you have made this one. Okay, now the next step is to you can use a field line here. Okay, what is the length of the field line? LF, and the width of the field line WF. Okay, so go to the table and see the values. What is the length of the ground plane? This one. Okay, 15.5. okay, and the width of the ground field line is 1 millimeter. Okay, so you need to, and from where it is starting from the center of the substrate, so you need to move your WCS at the center of the substrate. Okay, so you need to choose the brick and write here field line. Okay, and minus wf by 2. Okay, and in the vmax interaction you have the length of the field line. Okay, and tp thickness of the patch. Okay, now click preview, and what value you have of 1 millimeter of the width of this field line. Okay, and what is the value of the this is 15.5. okay, 15.5 millimeter of length of the field line. Okay, now click ok, and you can see here this is the field line. Hello dear Dundiana, where are you from, and did you register for it? This is the unknown person. I removed that person. Okay, so okay, we have designed the field line. Okay, now you can design these plastic elements. Okay, this is a technique to increase the gain of the antenna. Okay, or you can use plastic elements, okay, to increase the gain or to set the frequency, or there are so many techniques as I told you before, but in this study we will study about this. Okay, this is plastic element. You can also design dual band antenna without these plastic elements. Okay, I use these plastic elements in my paper to increase the gain of the antenna. Okay, and to get rid of the back radiation. Okay, so first we design these monopoles. Okay, so you see there are two monopoles. Okay, or you can say there are two resonator or two radiators. Okay, hello dear Dundiana, please can you introduce yourself, because I did not notice you have registered for the course. If you did not register, please leave this session. Can you hear me?
Mr. Sarosh,
Yes.
he wrote in the chat.
What?
He wrote his name in the chat.
Yes, let me check the chat. Okay, Kaiti. Why did you not join from the your register ID? That's why I told you to register with your registered name, so that it is easy for me to know you. Anyway, okay, let's continue. Okay, now we need to draw these monopoles. Okay, we have designed the field line. Okay, now we should start from this point. Okay, always start from the point that is very near to you, like you have designed the field line. Okay, what is near to the field line? This patch. Okay, so you need to draw this patch first. Okay, so you see w5 is this width. Okay, it means w5 is the width of the both side. Okay, on the both side. So you need to, and also you need to know the height, I mean the length of this patch. Okay, short patch. So w3 is the patch of the whole. Okay, width of the whole patch. Okay, so w3 and w5 just keep in your mind. Okay, so first see w5. Okay, so you need to, it means your your WCS must be at this point. Okay, at this point, can you see here, at this point? Okay, so you need to align your WCS at this point. Okay, like this.
Mr. Sarosh, I think it is better to start from the first design. I think this picture, I read your paper.
the first picture, I think in the steps for the design. If we do it, it become easy for us because we need to cut and something like this.
You mean like this?
Yes. If you start from this one, this evolution, I think it become easy for us.
Okay, I have don't have any problem, but you see, I am just checking the dimensions to exact dimensions, but here you
It's a final design, yeah.
Yes.
I know the final design, yeah. But it's become easy for us because yesterday we explained about the badge, and particularly also some people maybe first time to using CCT.
Okay, if you want, I can start from these steps. Okay, don't worry. No need. Don't worry. Okay.
Thank you.
Okay, so we need to we can design this patch. Okay, this is the length of the patch and this is the width of the patch, and you can see here what is the length of the patch and width of the patch. Okay, uh, I think this is the same. In the table, do we have? No, we don't have in the table. Okay, so let's start this one. The frequency may not be exact. Okay, it may be near to the frequency.
It is written in the paper, you know, after the equation 2, you have some description.
Yes, I am reading this. You can see.
Yeah.
Okay, so
I read it before. Yeah.
yes, thank you. Okay, so length of the patch is how much? 8.8 millimeter. Okay, but I am still afraid is that the exact values or not. Okay, so you need to create a small patch here. Okay, small patch that is whose have WP width of the patch. Okay, and minus LP. Okay, we don't need to divide this patch. Okay, because we are starting from the origin. Okay, now this point is our origin. Okay, so in the upward direction we need to write here. Okay, so we need to write in this box. Okay, it will ask you about the length. Oh, sorry, here I write WF. This is patch. Okay, and can anybody tell me what should be the value of the W max, if you understand the previous steps?
0.035. I think it's a thickness.
Yes, thickness TP. Is it positive TP or minus TP?
It depends on a line.
Minus.
You can see here this is yes, this is on the edge, so that's why you need minus TP, because it will go on the other side. Okay, if you use positive, then it will design on the field line, not inside under the field line. Okay, so now click on it, and the width of the patch is 9.8. okay, and the length of the patch is 8.8. okay, so this is your patch. Okay, okay, I take the some suggested values. Okay, not exact in the paper because we don't know these values. Okay, I did not add this dimension in the paper. Okay, so I take any dimensions just to draw this one and to set at dual frequency mode. Okay, so I take more values here, length of the patch here, 12.8 here. Okay, so in the next step you need to cut the patch. I mean yes, you need to truncate. Okay, these sides. Okay, these sides, and also you can see your field line cover this portion. Okay, so it means you need to add another patch. Okay, very small patch from this side. Okay, like this. Let me explain like this. You can write suggested values here. Okay, like this. and you need to write here minus TP. Yes, like this. Okay, so you need to add this patch and the other patch. Okay, now press shift plus button on the keyboard. Okay, so you can see both now become one patch. Okay, the other step, we have done the first step and the second step. Now in the third step we need to truncate these sides. Okay, the inner side and this side. Okay, so we first need to draw a box inside the patch. Okay, okay, so we are now in the let me check here, the length is 12.18. okay, so I move my WCS at this corner so that it will be at the center, and you can move your WCS at the center. Okay, so this is your center, and also click apply and rotate it. Okay, okay, now you need to create a box inside it. Okay, okay, so this is a small patch. This is like a box. Minus TP. Okay, now click OK and choose the patch and delete the box that you have designed. Okay, this one. Okay, so we have this one. Okay, actually in order to design the antenna, suppose you have the patch like this. Okay, suppose you have this patch. Okay, you first simulate this patch. Okay, and check the results. Okay, and then in the next step, suppose your results are not desirable, then you need to cut this patch from the center of this patch. Okay, this one, I mean this one. Okay, and you need to cut this patch here. Okay, now you need to cut these edges. Okay, and this one. Okay, minus TP. Okay, so click the patch and click minus and select this short patch and press enter, and the sides are now truncated. Okay, now this side. Okay, so you need to add this feed line and the patch. Okay, so that both will cut from each other. Okay, now you need to align your WCS at this position. Press escape button. Okay, okay, you need to see. Okay, okay, so you need to now delete or cut this patch from the monopole. Okay, okay, so you have a shape like this. There are two resonators. Okay, first you need to simulate this design. Okay, and then you will check the results. Okay, and also I will show you how you can see graphs, many graphs in one folder. Okay, like many graphs. Let me show you now. First we create a port here. Okay, you can take approximate values. okay, or it is mostly 2 times of the WF, not 2 times. Suppose I have created this port, okay. If you set this port at 50 ohm, okay, then the size of the port will not affect more, okay, like this one, okay. Then it will set 50 ohm port, then the shape or the size does not matter. Okay, I simulate this one first and check the results, and then we will do further modifications. Did you try the previous lecture, as I told you to check the parametric sweep and the designing ports and to check the adaptive mesh?
Mr. Sarosh,
Yes, please.
why the port is extended?
In the CPW technique, you use half of the port on the other side, and you can say 20 to 30% on the other side, okay, in the CPW, because in the connector you see, if you have a full ground plane, then you connect the connector on the, I mean, solder the connector on the other side, okay. But in the CPW you use half on the other and half on the other side, okay.
Okay, and why you use coplanar waveguide?
This is coplanar, okay. This is you can see here, this is the ground plane. You can see the radiator and the ground plane are on the same side of the substrate, so this is CPW technique, okay, here. And you
Yes,
use,
I know. I mean, why you use this technique?
okay, actually I am following this paper. Did you see this one? Okay, I can also use the ground plane behind the substrate, but you can see, if you use the full ground plane or partial ground plane, then you will not get the desired results, okay. It's up to you what you want. And the other thing is important thing that this paper is starting with meta surface base, okay, with single layer compare, okay. So if you notice meta surface base, meta surface do not do not affect that designs that have the full ground plane behind the substrate, okay. So in order to design the meta surface, your antenna must do not have a full ground plane, okay. So because you see in the behind of the substrate, if there is a full ground plane, then meta surface will not affect of that design, okay. That's why in this paper I use this CPW technique, so that the other side of the antenna will be empty, okay, and the meta surface will have impact on it.
Okay, thank you.
Mr. Sarosh, excuse me,
Yes.
could you write in a PowerPoint how to adjust the size of the coplanar, the feet? Just explain to us.
This one you are asking about?
Because you said half, because it's totally different. But in the macros, I think there is also calculation for it.
Yes, I will send you the formulas, okay. There are some special formulas for this one. I will send you, okay.
No, but I mean about the size of the board, which you adjust now. If you can explain to us.
I have one design, okay, in which I have set the I use formulas, okay, like there are some formulas you write directly in the waveguide port, okay, like suppose like this. Here you write the formulas, okay, of using WF, using LF, using height of the substrate, okay, and you write here the formulas, and it will directly calculate the dimension of the port, okay.
This is for the coplanar, yeah?
Yes.
Please send to us this screenshot for this formula, please.
Yes, I will send you formula, okay. And you can
Thank
see
you.
here, and as I told you, it will not affect size of the port. It will not affect if you set the impedance at 50 ohm, and you can see it is the results are near because the antenna is dual band, and you can see it is at near to 2.45 and it is near to 5.8. okay, you need some adjustments to set the frequency bands. Okay,
Thank you.
but if you want formulas, then I will send you. Okay, you need to then in order to implement the formulas, you need to write the WF and LF in this box. Okay, as you know how to do it. Okay, and then
I get used to make it for the normal feeding. Yeah, I get used to do it.
okay, I will write the formulas and will send you. Okay, on WhatsApp. Okay,
thank you.
Mr. Charles, can you please show us the reference impedance?
Yes, this one.
It's 15.
Yes.
Dark.
Yes, because I use this one. As I told you, you can use this one. Okay, to set impedance at 50 ohm.
I always use it and check it also.
Okay.
It's better, yeah.
Yes, we must make sure, because some people do not use this one, and and also do not check the reference impedance, and their reference impedance are about 65 or 70 when they send the design for fabrication, and there is a lot of yes, so you need to make sure this one. Okay, one person have a question. Yes, I will email the formulas to all of you. Don't worry about that. Just you need ask me on the WhatsApp. Okay, to remind me. Okay, about meta surface, was it, and where is this meta surface using this design. Actually, I am just following this paper, as I told before starting this lecture. I told you we our main focus is the dual band antenna for today. Okay, we are not designing meta surface and for off body communication. Okay, but in the next lecture we will discuss these things in detail. Okay, so today we are just discussing the dual band antenna. Okay. Okay, you need to see the surface current also, so that you may know which part of the antenna has impact on the operating band. Okay, so you can also animate the antenna. Okay, you can see here there are option of animate field. Okay, and also in the paper you see also, let me show you like this. Where is the surface current? This one. Okay, some people like to have graphs like this. Okay, surface current, so I have taken these pictures in the CST. Okay, so I show you how you can find these type of surface current, but here you can see the arrows. Okay, okay, so you need to just stop the animation, and you need to complete this one. Okay, at this point. Okay, and here you can see here contour. Okay, you need to click on the contour, and you can see here if you have latest version, then it will show you some green color. Okay, like green color, but here you need to just rotate your antenna. Okay, like you can use perspective view. Okay, here. Okay, like
actually these are drawbacks in this version. I know that I have the old version. We can take a very good pictures.
Yes,
you need just to do that. Yeah,
yes, and you can just increase your
yes
to see the red portion. Okay, like this, and you can also remove the box, this box. Okay, and you can take snap here. Okay, and add in the paper. Okay, and other thing, now you can see here where is the red portion. The red portion is affecting this point of the field line. Okay, and also the ground plane. Okay, okay, so also you need to add some small short patches. I as told you, in this design I have used the plastic elements. These are the plastic elements. Okay, to increase the gain and to just set the frequency bands. Okay, but we will see what will be the effect on the frequency if we increase or decrease this width. Okay, so in order to do parametric optimization, you need to add some slot here. Okay, there are many ways to do parametric optimization, like you already set the dimensions here, and just you need to go here and to find the values, and you can do parametric sweep directly. If you don't find any, or you are not able to do, then you need to create a very small patch. First you need to know the dimensions of this line here, 4 millimeter. Okay, so you need to create a very small patch here of the same length. Okay, minus 2 and minus, you can write here any you can assign any value, digit, I mean letter here, okay, like q, you are assigning its value is 0.5, okay, 0.5. okay, now press the minus tp, okay, and do it on the both sides, okay, also on the other side. Okay, now minus v minus q, okay, the same, minus tp, okay. So you can see here, you will find a letter here, q, okay. If you press 1 and press F7, you can see it is increasing or decreasing, okay. So in order to do optimization, you need to go to the home and click on the parametric sweep, new sequence, new parameter, select the q, okay. And from where do you want to start? I want to start from 0.2. I want to simulate it 3 times, okay. So do 3 simulation. It will take sample with 0.2 millimeter, 0.4 millimeter and 0.6 millimeter, okay. I click start and it will do, you can see here it is increasing per simulation, okay. It will do 3 simulations and the 3 simulation will be on the same graph, okay. And you can see the difference of because you know, with the surface current this portion is highlighting with red color, so it means if you change this position or add or do subtract any slot or add any slot here, then you will have difference in your frequency bands. And the other okay, I don't have any other simulated design, so I need to do simulation. Okay, if you want to see the graphs, I mean 2 to 3 graphs in one folder, then you just click on the main branch, okay. You can see 1D results and click the right button of the mouse and you need to click on the new tree folder, okay. Here is simulation is running, so that's why you are not able to click. After completing the simulation, you can click on this new folder, okay, new tree folder, then it will create a new folder in this branch, okay. And like this, okay, like this is with name new folder, okay. So you can write any name by pressing F2, okay, of the keyboard, and you can write the name of the folder, and you can just suppose you have this graph, you can copy this graph and paste in that folder that you have made, okay. So in this way you can see many graphs, okay, in one folder. The other thing, if you want to draw this S11, like you have this S11 and you want to draw in another software, so in order to draw another software you need to export this file, okay. Like you can go to the post processing, okay, and you need to wait a minute, okay, you need to go to, select this S11, okay. Then you need to go to the post processing, then go to the import and export. Okay, just keep in your mind there are 2 types of import and export in CST. One is in the modeling, okay, and the other one is in the post processing, okay. This in the post processing, the import and export you have just to import the file, export the file, okay. Like to S11, click on this one and you can click on the this one, okay, plot data, ASCII data. You can export this data, okay, and you will have text files on the desktop, okay. And then you can plot in another softwares like you can draw in Origin Pro, Sigma plot, or you can draw in MS Excel, okay. And one more thing, you cannot even make any design in the first step. Okay, so you need to do multi simulations to set your design or to make your design to achieve better results. Okay, you can never make design in the first attempt. You need to do multi attempts. Okay, so you will be able to make a good design. Okay, for the next day I want from you to design a new shape. Okay, and you can use any feeding technique, like you can use CPW, you can use full ground plane, you can use half ground plane on the behind the substrate. Okay, and you need to show me the results. Okay, if the results are acceptable, then I will approve your design, and I will tell you to save that design for further working. Okay, like for writing papers and other things. Okay.
Mr. Ahmed,
Yes.
can we know the impedance of the patch in CST?
It is simulation running. Maybe yes.
I mean the patch, impedance of the patch, not the feed line.
Actually, this is the impedance of the whole design. Okay, but in order to see the impedance on the I am not sure here. You will find option here, but
So
in the
we
Z
have just a formula.
yes, we just have a formula, but here I don't have any option. You can also check here, but this will tell you only the impedance of the design. Okay, like you have a dual band antenna, one frequency is resonating at 2.45, and if you zoom this one, okay, then you can see, for example, at 2.45 you have an option. Okay, like 2.45. Okay, here is 2.45. Okay, and you can see impedance is close to 50. Okay, but it is to
This
50 ohm.
impedance is for what?
This is the there are two ways to see the impedance. Okay, this is the impedance at the desired frequency band. Okay, like this one is the whole design, but the Z matrix, in the Z matrix you will find at the each frequency band. Okay, like at 2.45 you can see, and you can see at 5.8. Okay.
Okay. So this graph is the impedance of the patch at the edge or what?
This is only of the dual, like you have a dual band, then it is the frequent it is showing you the impedance of at each frequency, like at 2.45 gigahertz it is showing you. Okay, you can see here, and also you can see on the other band. Okay, to see either it is 50 ohm on the both frequency bands or not.
And for reference impedance?
For reference impedance it will give you for the whole design. Okay, like it will not properly tell you about at which frequency band. Okay, but in the Z matrix you can see very easily at each frequency band. Like you have a 2.45 gigahertz design, then you can see what is the frequency band, I mean impedance at 2.45. Okay, and what is the impedance at 5.8 gigahertz.
Okay, okay. And can we change the polarization of antenna?
What do you mean by polarization? Yes,
From linear to circular.
yes, we can. Yes, you have to see the surface current. Okay, in order to check the polarization, there are two ways to check. The first one is the surface current. If your surface current is moving in the circular direction, like it is your, you can see your surface current is. Let me draw here.
I mean, how to know is this polarization of antenna is circular or
Yes,
linear?
I will tell you. The first method is the axial ratio. Okay, with axial ratio graph. Okay, if the graph is less than 3 dB, okay, then you can say your design is circularly polarized. Okay, the second method to check the surface current. Okay, surface current. Okay, if you need to check if your surface current is moving in the circular direction. Okay, it can be clockwise or it can be anti-clockwise. Okay, like this. Okay.
In CST.
Yes, it is called LHCP. Okay, left hand circular polarization. Okay, LHCP. Okay, the other one is called RHCP. Okay, right hand CP. Okay, right hand circular polarization.
in HFAS.
Yes, let me complete the simulation, then I will show you in the surface trend.
Actually, Mr. Sarosh, actually, we depend totally upon the axial ratio.
Yes,
In my case.
yes. We totally depend. Okay, I told you there are two cases. Okay, if it is moving in the circular, pattern, then if it is not below 3 dB, then it is not called circularly polarized antenna. Okay, so this is the must, you must fulfill this condition. Okay, the axial ratio must be less than 3 dB.
Mr. Ahmed, after finish the simulation, can we show us the second method?
Okay, yes, I will show you both.
Okay, thank you.
Because this design is not a circularly polarized. Okay, but we can check whether it is circularly polarized or not in this field. Okay, so there are so many ways to make the antenna circularly polarized. Okay, you can see, I will send you my papers. Okay, I have some papers on circularly polarized antennas.
Sarosh, in your paper, when you are estimating the electric lens in lambda, I think you take the highest frequency, yes? 5.8, something like this. I remember that.
In this paper,
Yes, the electric lens, I think you depend upon the high frequency, 5.8, I think.
no, I use the 2.45 gigahertz.
For electric lens, you choose, I think, estimating using the higher frequency, yeah? 5.8.
In most of the cases we use the lower frequency bands. Okay, you can see here guided wavelength at 2.45 gigahertz. So all the designs, I mean for all the dimensions, I calculated at 2.45 gigahertz. Okay.
Yes. Thank you.
So don't worry, we will study each and everything, and because our main target is to writing each and everything. Okay, to first, in order to write the paper, we must have a design. Okay, good design, then we will study the graphs, then we will study how to write this paper. Okay, and I will help you and guide you, don't worry about it. Okay, so now the simulation is completed.
Hello.
Yes.
Sir.
Yes.
Sir, can we draw a equivalent circuit diagram of antenna on the CST? Is any kind of method is there?
In CST you cannot. Okay, I mean you can use lumped elements, like you have many things here. Okay,
Okay.
but you cannot like this one, circuit elements. Okay, you can see here you have a diode, but you cannot properly design here the circuit model. You need to use other software like ADS software. You can use AWR softwares. Okay, to design this equivalent circuit model. You use these things.
Design those software, and then we can draw the equivalent diagram of that.
There are many ways to draw the equivalent circuit model. In this paper, I draw the equivalent circuit model of both designs, for the dual band antenna and for the meta surface.
Yeah, this one.
Yes, but I suggest you to use AWR, or you can use ADS. Both are good softwares. Okay.
Okay.
Okay, in the reconfigurable antenna we will study these things. Okay, how to connect these elements here. Okay, because in reconfigurable antenna you can use, because here you can see, if you zoom this one, this is your antenna. Okay, this is your antenna. So it means you have to connect your antenna with these things, because if you want to draw the equivalent circuit model, and you must have to connect this antenna, so surely your results will not be good if you connect your antenna. Okay, so you need to use other softwares. Okay, so we have S11. Okay, you can see here there is not much big difference in the frequencies. okay, with q is equal to 0.2, 0.4 or 0.6. okay, so you need to if in this case you need to take the higher values, like first simulation is 1 millimeter, okay, the second simulation is 1.5 or 2 millimeter, and the third simulation is at 3 millimeter. okay, so in this way you can see the big difference. okay, because we are taking samples at 0.2 millimeter and then 0.4 millimeter, only 0.2 millimeter difference, so in this way we are not able to see clearly. okay, but
actually, the rules, sometimes when we make this kind of optimization, parametrics web, actually we take a very big step. After that, we try to reduce our step.
yes, but yes,
we do it many times. It cannot come from this time. Yeah.
yes, but now just see, notice one more thing. okay, now you can see here, if you put the value of q is equal to 0.2 millimeter and then go to the 0.6 millimeter, and then you can see your frequency is shifting towards higher frequency. okay, if you reduce the size, I mean if you if you cut, you don't need to extend this patch, you need to cut this patch. okay, this patch. okay, this patch. okay, you need to cut this patch. If you cut this patch, then your frequency will move on the other side. okay, like on towards the lower frequency band. okay, in this side. okay, so if you extend your design, then it will move towards the high frequency. okay, so you notice this thing. okay, so in this way you can you may know what you need to do. You need to cut this patch. okay, this patch, no need to extend this patch. okay, in the surface current we have a like 2.45. You cannot see circular polarization, I mean the arrows in the circular pattern, so you need to use these arrows. okay, so that you can able to see. okay, if you see your arrows are going up and down. okay, like if you notice from far away, you can see your arrows are going up and down, up and down, so it means they are not in the circular pattern. okay, so check at 5.8 gigahertz, so you can see it is showing like a if you zoom your antenna, you can see your arrows are moving in the circular pattern. okay, so it is showing little behavior of the CP. okay, now check the axial ratio. okay, yesterday there were not options available here, but now it is available. okay, you can see here there is a option of the axial ratio. okay, so you need to see the Cartesian yes, you need to see the Cartesian plot. okay, to see whether the it is below 3 dB or not. You can see it is at if the it is linearly polarized, so it will be 40 dB. okay, but in the case of this one, you can see it is still 40 dB, so means no polarization behavior.
So it must below or above 3
yes, it must below 3 dB. okay, so you can see it is 40 dB but not below 3 dB. okay,
Sir, any method to make circular polarized antenna? Anything?
yes, there are so many ways to design circularly polarized antennas. okay, I some of my design are not published, so I am not able to show you, but let me check if
I think one of it, if you got the opposite edges.
let me explain. okay, there are so many ways to make the antenna circularly polarized. okay, what is the main condition to make the antenna circularly polarized? Suppose your current is passing in this way, okay, in this direction or in this direction. okay, this is called linearly polarized, but you need to convert your pattern into circular pattern. okay, so how you can make it? okay, suppose you have a field line. okay, like you have a field line with this. okay, suppose yellow one is your field line. okay, and your current is moving in the, surely it will move in the upward direction. okay, but if you make the edges like this, okay, you need to create a 45-degree angle, okay, of the slots. okay, you can see here it should be 45-degree angle. okay, to convert your surface current in this way. Okay, so in this way you can create another patch, okay, that will move in this direction, okay, and it will be, and then you can convert it. Okay, you need to make a patch. You can also cut this patch, I mean edge at 45 degree, okay, and you need to turn your surface current at the angle of 45 degree. When it will move at a 45 degree, then it will move, try to extend your patch in the circular, or in by adding 45 degree slots, okay, so you can be able to turn your surface current in the in circular pattern, okay. Or also it is easy to achieve circular polarization with the CPW, okay. You need to modify this shape, like for now I cannot show you my designs because they are not published yet. I hope inshallah it will be published in few days, then I will show you, okay. But I can show you one of my paper that is accepted, okay. Where is that? Okay, so this is my paper, and this is the design, okay. You can see here this is a single band antenna, but I have modified the shape of the CPW, okay. You can see I make 45 degree, okay, and also I truncate the patch at 45 degree, okay, and it is showing a circular polarization behavior, okay. You can see in the graph, okay. So this is the steps I designed, okay, and you can see axial ratio is below 3 dB, okay. This is, you can see the 3 dB line, okay. This is the 3 dB line, okay. In the first case, this is the first case, I designed a simple patch antenna, okay, but the axial ratio is 40 dB, okay. Then in the second case, you can see it is showing blue color. You can see the blue color, okay, the blue color line, okay. It is below 3 dB but not at the desired frequency band. So what I have done, I have truncated the ground plane, okay, and the frequency is shifted towards the desired frequency band, because my antenna is also at 2.45 gigahertz frequency, okay. And you can see in this way when I added slots, and you can see there is a big difference, and there is a wide axial ratio, okay, and it is below minus 3 dB, oh sorry, 3 dB. So in this way you can achieve your, and also I show you the surface current. This is the surface current, okay. So you can see in the ground plane you also have some circular pattern, and the surface current, okay, flowing in the circular pattern. And also in the patch, in the first patch, you can see when the current flow, then it moves here a circular pattern, okay, in the half patch, okay, and in this side it is showing it like this, okay. You can see this more clearly when you do animations, okay, in the CST.
Thanks, Mr. Shash, thanks.
Okay, so in the next step you understood the way of designing, okay, and you can add plastic elements. Also you can add this is called plastic element. What is plastic elements? The element that you add on the patch, or on the behind the patch, I mean behind the substrate, but it is not a part of the radiator. So this is called plastic element, okay. So you can say additional patch, okay. This is not a part of this radiator, okay, but it helps you to increase the gain, it helps you to set the frequency band, okay. It helps you to improve the radiation pattern, because yesterday we noticed one thing, that we are using the CPW, and with the CPW it is showing a very back radiation. So in this case it is not a very back radiation, but I also, other thing I told you, if you are using meta surface, you cannot if you have full ground plane behind your antenna, behind your substrate, then meta surface will not affect your design, okay. So therefore there is a condition to use the meta surface. You must use CPW, or you can use a partial ground plane behind the substrate, okay. Okay, in from tomorrow, for the today for the tomorrow task, I want from you to make any shape. Okay, but the shape must be somewhat easy to understand, not a very complex shape. Okay, the new shape, and you need to design. Okay, I will tell you, for the papers you need to design that kind of antenna, and for that you can do design steps. Okay, like this one. Okay, you have a design and you are easy, you can do design step, like I do this, do this, do this, and then this. Okay, your antenna must not be consist of only one design step. Okay, like very simple antenna and you cannot do design steps. Okay, for the paper it is necessary to add the design steps. Okay, for if you want to target good journals. Okay, so it is better to make a new shape. Okay, you can apply any technique. Okay, also I use this technique. Okay, let me explain this paper. Okay, I will show you why I add these plastic elements and why I add these circular rings. Okay, first I noticed one thing, when I design this simple patch, then my design be showing behavior like this. Okay, you can see the pink color, this one, ant one. Okay, it is resonating at 2.5. Okay, but the other band is not working at the 5.8 gigahertz. Then what did I do? I truncated these sides. Okay, and you can see the blue color, the 2.5 still remain the same, but the other band is shifting towards the desired band. Okay, at 5.8 gigahertz. Then in ant 3, what I truncated the patch. Okay, and you can see also this one is shifting little bit. Okay, because I need a 2.45 gigahertz, and while the other one is shifting towards 5.78, or 5.82. Okay, but the return loss is not very improved. Okay, so then in the final step I added the these plastic elements. Okay, and you can see this is the red color, it is perfectly resonating at 2.45 gigahertz and 5.8 gigahertz. Okay, so this is a dual band antenna. Okay, so in the paper you also need to do optimization. Okay, like in the simulation you do optimization, then also in the paper you need to add the optimization graphs, like why I added these plastic elements, why I use these circular rings, why I added these plastic elements. Do you want to say anything? Dear Tijraj, please turn off your microphone. Okay, so in the paper you also need to add the optimization graphs, as I told you, like this. Okay, let me show you. Like this is, dear Munip, if you have any question, please ask. But if you don't have, please turn off your microphone. Okay, so I did this. You can see I have added so many optimization graphs. I did parametric study for the L3. What is L3? You can see here, what is L3? This is L3. Okay, so what will happen if I increase or decrease the size of this pole? Okay, so you can see in the graph, this graph. Okay, you can see my both frequencies are shifting. If I you can see there is a gap of one, I think about 1 mm. Okay, so you can see both bands are shifting if you increase or decrease. Okay, so in this way it is easy to know for you what will happen if we decrease the length of the pole. Okay, like if I use 3.8, then you can see it will resonate at 2.3 gigahertz, and 3.8 means blue color. Okay, so blue color is this one. Okay, dark blue, it will resonate at 1.5 gigahertz and 4.8 gigahertz. Okay, if you increase the length of the pole, then you can see your frequency, both frequency bands are shifting. Okay, towards right side. So it is easy for you to understand the design. Okay, the other optimization graph is done for the W2. Okay, what is W2? In the design you can see W2 is this one. Okay, length, width of the pole. Okay, so if you increase or decrease, you can see the graph, you can see this one. Okay, so in this way it is necessary to add the optimization graph. Okay, this is for the IEEE. Okay, so it is in IEEE always demand brief explanation, so you need to explain your design in each I mean in every situation, like what will happen if you do this, do this, do this. Okay, and also I added optimization graph for this one. Okay, like if I increase, I mean this is the distance from the top of the substrate and this point. Okay, this is called RL. Okay, so length of the rings. Okay, so what will happen if I move these rings up or down? Okay, so I added this parametric optimization in the graph RL. Okay, so you can see if I increase the distance, then it will, you can see if I first I simulate at 11 mm distance. Okay, I mean height, so it will resonating at this point. Okay, so if I decrease the uh, length, then you can see your frequency is shifting towards right side. Okay, so it is very important to do the optimization. That's why I told you to, whenever you design, you must need to do the optimization. Okay, and for these graphs, you know, for these graphs you cannot directly draw this in CST. So in each optimization you need to save the graphs. Okay, like let me show you. Okay, like this. Okay, you go to the 1D results, click on the new tree folder, and you will find a folder like this. Okay, for like you want to do optimization for the length of the pole, okay, or length of the patch, you can write here LP. Okay, suppose you have find graphs. Okay, here you can paste here. Okay, like this. Okay, you can paste graphs here. Okay, and later on you can, once all the simulation is done, you can export these graphs. Okay, in the post processing. Okay, you can go to the import and click on the plot data ASCII, and click on the desktop, and you can write here LP, and write the name of the thickness or millimeter. Okay, like you have done for suppose 0.2 millimeter, you can save the files like this on the desktop. Okay, and later on when you done all the simulation, then I mean use or export all the graphs that you have done from the optimization, and then you, when you have time, then you can draw all the graphs in the Origin Pro or in the Sigma plot or in the MS Excel. Okay, I use the Sigma plot for these graphs. Okay, for these optimization graphs. And
Mr.
also,
Ahmed,
yes, please.
sorry, but for the picture of antenna, did you export it from CSC or design it drawing in Visio or MS PowerPoint?
At first when I designed the antenna, then I try to just to have a screen like this. Let me show you. At first I just try to take a snap. Okay, with snipping tool, you know, snipping tool.
Yes.
Okay, I try to take the snap of this one. Okay, but I noticed thing that the picture is not very high resolution. Okay, sometimes most of the times I use snap tool. Okay, snipping tool, but in this AAA paper I draw these figures in the MS Visio. Okay, I draw these pole. Okay, then I added all these patches. Okay,
In PowerPoint or MS Visio?
you can use PowerPoint. Okay, you can use PowerPoint. I use here the MS Visio. Okay, MS PowerPoint is also a good option. Okay, I draw this, like I create a very small patch, like let me show you. Okay, so like this you can paste here the graph so that you can remind your design. Okay, and you can use the patch here. Okay, on the you need to create outline on the patch. Okay, like this. Okay, you can change the color. Okay, like this. Okay, you can use black color, oh sorry, shape this and outline some dark color with dark color. Okay, like with red. Okay, so for this patch, small patch, you can use like this. Okay, and for this you can again do like this. Okay, like this. Okay, then you can add all the patches later on. There is the option of merging. Okay, or creating group. Okay, like this. Okay, so you can see there is small outline, so you need to delete the outline. Okay, you need to delete the outline, no outline. Okay, and you can give the color yellow. Okay, like this. Okay, and this one, in this way you can draw. Okay, like this. Okay, in this way you can you once you complete, then you select all the things and click the create a group. Okay, like this. And when you want to paste in the Word file, then you need to save it as a picture, not a, like if you paste then you can edit this one, but you need a picture. So you will find option in the below like this. Okay, and you need to click on this picture. Okay, then it will become a picture, high resolution picture.
And for arrows?
What?
For arrows? For dimensions?
Yes, for the arrows. Yes, for the arrows you can use arrows here. There are a lot of options here. You can see here like this. But this is not our today lecture. I will explain in the coming lectures.
Actually, to use it as a Visio, they also
yes,
they have
yes,
have option to use a dimension. It's very nice option.
Yes, I use MS Visio. That is very nice, but now it is expired. I will try to.
I use it
yes.
originally.
Yes, it is very good software. Okay, so
and you have the option for the arrow. You can just similar to CST. Just you can have this arrow, something very nice.
Yes, yes. And also for the 3D pictures you can take up snap tool like this. Okay, you can take snap by doing like this. Okay, you
Mr. Ahmed, can you please explain MS Visio in the session of graph?
Yes, I will explain. Now it is expired. I will try to again activate this tool. Okay, and I will explain in the graph. Okay,
yes,
don't worry.
Yes, please, Mr. Ahmed. Yes.
I will explain. Don't worry. Okay. So because my main target is to let you able to write research paper. So for sure I will tell you each and everything, how to draw graphs, how to make arrows and everything, how to write papers, and each and everything I will explain. Okay.
Okay, thank you.
So okay, so for the next lecture, I mean for the next day, I want from you, this is an individual task. Okay, you need to design an antenna. Okay, and then you need to show me the screen to show your designs. Okay, and you need to show me the S11. Okay, at which frequency you operated the design. Okay, you need to show me the efficiency. Okay, and you need to show me the VSWR. You need to show me the reference impedance. Okay, then you we will check whether it is circularly polarized or not. Okay, and then also you need to show me the radiation 2D radiation pattern. Okay, like this, realized gain. Okay,
at what frequency?
I want from you to design at 2.45 gigahertz. Okay, and using FR4 substrate. Okay, using FR4. This I use this FR4 because this is cheap material and it is easily available everywhere. But if you use Roger, then sometimes it is available, sometimes it is not. Okay, so if someone has achieved very good results with good design, then I will approve that design and I will tell that to save that design for the coming papers. Okay, and I hope you
for complex or simple design.
Yes, the design must be new, no any following any paper. Okay, you can make any new design. Okay, you can use any technique. Okay, I just teach you everything like designing ports and creating field line, and you can use this curve tool. Okay, also, and you can make any shape, like you can also use a circular shape. Okay, because here it is a monopole, but you can also use a circular shape. Okay, and you can also use elliptical cylinder. Okay, elliptical cylinder is also a very good option. Like first you need to, like I want to design a patch on the behind the, like I want to design a patch here, suppose. Okay, let me, okay, I want to use this elliptical cylinder. Okay, in this way what you can do. Okay, let's see. Okay, so you have a U radius, means it will expand your circle in the horizontal axis. Okay, and it in the V radius, it means it will expand your circle in the V direction. Okay, like this. Okay, like this. Okay, So now you can see u radius. In the u radius it is expanding your circle in the horizontal axis, okay, and in the v radius if you increase it then you can see like this, okay. You can also, okay, you can use any, or in the v center you can see if in the v direction if you increase this one then it will shift your circle in the upward direction like this, okay. If you use -2 then it will move downward, okay, like this, okay. And you can use TP, thickness of the patch, okay. Like you have a shape, okay. How to create a new shape, like you have this one and you want to make a slots, okay. You can use you can use anything you want, okay. Like you can use this one, curve tools, okay. For this one you need to use this plane, okay. So I want to create a slots in different planes, okay. Like I'm using this one. You all can create outline with this one, okay. Not only for designing the patch, you can also use this outline for creating slots, okay. Like I want to create a slot, but you must keep in mind you must combine your points starting and ending point, okay. Okay, suppose I draw this shape and I want to cut this shape. You need to first convert into the patch, okay. Just preview and check whether it is inside the patch or not, okay. Now you have this slot, okay. Now you need to select this circle and press minus button on the keyboard and select the slot and press enter, okay. So you can create slots whatever you want, okay. So did you understand the procedure? For the next lecture you need to show me different shapes and you need to operate your design at 2.45 gigahertz, okay. So let me write down the task here, what I want from you for the next lecture. I want from you to design a new shape, okay. Frequency at 2.45 gigahertz, okay. And use FR for substrate, okay. Thickness 1.6 millimeter, okay. And you can use any fitting technique, okay. Technique you can use CPW technique, can use full ground plane, okay. You can use partial ground plane, okay. You can use modified ground plane, okay. Okay, now the other thing you need to show me the S11, okay, of the design, okay. To show me the, and I will to show me the reference impedance, okay. To show me the what are the other thing, VSWR, okay. To show me the efficiency, okay. To show me the radiation pattern, okay. Okay, I and one more thing, I just I'm going to explain it. To show me the frequency, oh sorry, total efficiency here I think don't think let me simulate this one so that we will okay, to show me total efficiency versus frequency graph. Okay, I will show you in CST how can we draw these graphs. Okay, to show me the gain versus frequency graph. Okay, in CST you can also draw realized gain versus frequency graph. You can make IEEE gain versus frequency graph. You can make directivity versus frequency graph. Okay, I will show you from where you can draw these graphs. And once we I will try to teach you in the next lecture about circularly polarized antennas. Okay, and then I will show you how to draw the axial ratio versus frequency graph. Okay, in CST.
And Mr. Sarosh, and also for the gain versus frequencies.
Yes, I write here.
Okay.
So you need to show me these things. Okay, I will take snap and send in the group so that you will know these things. Okay, you need to just see the axial ratio graph. If it is less than 3 dB, then tomorrow lecture I will show you how can you achieve axial ratio versus frequency graph. Okay, and next coming lectures are very interesting lectures. Okay, day by day we are going to very interesting lectures. Okay, like flexible wideband human body antennas and implantable are very interesting topics, and also the electric resonator antenna, it is very interesting topic, and also MIMO and antenna arrays. I like these topics. If you have any question, please.
Sir.
Yes.
So for a paper publication, actually we require some kind of mathematical justification or also for
Yes.
the design or not?
Yes.
Okay, just for the optimization.
You can see while designing this antenna I did not follow any mathematical equation, but in the paper I added these things. Okay, you can see equations because this equation
Okay, means
only of
we
the
need to add, and after that the optimization result may be different.
yes,
For different dimensions.
these equation just for this one. Okay, because
Okay.
your design is starting from the patch antenna. Okay, then you modify the shape. Okay, that's why for this one you can say you are following this mathematical equation like this. Okay, but I told you before while designing your antenna you need to follow the research paper. Like this is a research paper, and you have seen the results. Like you can see in the previous research the design was 50 cross 50 millimeter square, and then 80 cross 80, and then what I designed is 44 cross 44, even achieving the same frequency band 2.45 and 2.45. Okay,
Okay.
your results must be somewhat improved from the previous research. Okay, like I claimed in this paper that I have achieved antenna, I mean dual band with a compact size even with the meta surface. Okay, because to achieve I mean for the meta surface the size is very compact, that's why I claimed that this thing. Okay, and also the gain is improved and the bandwidth is good than previous research. Okay, and also the SAR values. Okay, we will study SAR values, how to calculate specific absorption rate values when we study human body antennas. Okay.
Okay.
in human body antenna we will also study wearable antennas. Okay, that is very important part.
Okay, thank you.
We need to do many things in less time. Okay, so you must show me this one. I mean, the next day you need to show me this one so that you will be able to start with the simple design procedure. Then we need to move forward towards the complex designs. Okay.
Mr. Ahmed, I think it will be take more times because you design a new design.
No, it's not a big problem. No, don't worry about the new design. It's up to you. You can use or you can draw your shape in your on your paper with pencil, and then try to draw the same as in the paper in the CST.
Mr. Ahmed, in your design, here in your design,
Yes.
your design behind the antenna, new design, I think. For that, it will be take more time.
Yes, for actually designing antenna not take much time, but to optimize and to set the results takes time. Okay, this is the thing.
I mean here in CST, not in the article. In CST.
Yes, because I am explaining you. If you
Yeah.
only focus on the designing, then you can design in less time. Okay.
Yes.
What is the question in the chat? Yes, I will send you my article, this article. Okay, don't worry. This is another good design. You can I will send you also this paper. You can see this is very, you can see the design is very simple. Okay, but what is the novelty? You can see here nobody has done this structure like this. Okay, to divide the field line into two parts, and then even they are not connected with each other. Okay, and this is the circularly polarized antenna. Okay, dual band circularly polarized antenna for wearable applications. And there is a full ground plane, just a U-shaped slot inside the ground plane.
Mr. Ahmed, for this image, how the antenna is hidden?
Waveguide port, okay, with waveguide port here and the field line, okay, and you can see there is a.
Because it's not touch.
Yes, yes, it is not touch, but it is very near to like you can say it is of about 0.2 millimeter gap. Okay, so in this way you can see the surface current is also flowing on the other patch. Okay, like this on this patch with the, if it is very near. Okay,
Okay.
because this is a part of one layer, not other layers. Okay.
Okay. And how to know the equivalent circuits?
I will try to arrange one seminar on the equivalent circle model. Okay, I most of the papers I added equivalent circle model. Even for this paper I designed this circle model, but I don't have ADS software right now because it takes much space. I deleted this software.
Yes, just the steps. Can you tell me the steps?
Not one step, there are many ways or many steps to design the circuit model. Okay, like I think you can design the I mean you can export the SAP file, I think, or you can import the SAP file in the ADS software, and then in ADS software converts your SAP file into lumped elements like capacitor, resistor, inductors, with so many inductors. Okay, then you need to connect them each other, and then you need to simulate and check the S11. Okay, and then you need to compare your S11 with your with the design S11 of your design, and then you can, if it is very close, then you claim that you have achieved the equivalent circuit model. Okay, and also if you don't want to import the SAF file, then you can directly go to the ADS software. Okay, look the number of slots and number of parasitic elements in the design. Okay, according to that you need to, like, you have one resonator, you can say that with one RLC circuit you will have one resonant frequency. Okay, if you have two or more than three, then you will have multi frequency bands. Okay, in the RLC, in the equivalent circuit model. And then also you need to add the some inductor capacitor in parallel or in series. Okay, to set your frequency band. Okay, like S11. Designing circuit model is same as in designing the antenna. Okay, so you cannot even design directly, you need to do multi simulations. Okay, it takes more time than designing antennas.
Okay, okay, okay. Excuse me, Mr. Sarush. I want to ask about use some equation to draw some shape in the patch. Can I do that in CST?
Equations, you mean with you mean the designing the shapes with equations?
Yes, yes. According to question, drawing that maybe I want to exponential like draw for equation exponential to draw exponential graph like that.
For the graphs, I will show you this one, this result template. Okay, you will have results according to your desire. Like as I told you, this one and so many other graphs. Okay, there are so many options in this result template. I will show you. Let me complete this simulation. And for the equations, you can add some equations, but not very complex equation, because this is not a mathematics. This CST software sometimes do not understand like under root and other things. Okay, so you need to check these things.
Thank you very much.
But for the simple addition, multiplication, division, like this, it understand. But for complex mathematics, CST does not understand.
Thank you very much.
Okay, so you can also see this shape. Okay, the same as previous one, but this is circularly polarized antenna. Okay, so you can see I use the CPW. This is the conference paper. Okay, and I use the circular rings behind the antenna, and you see the size of the antenna is very compact. Okay, it is I think 5 cross 3 millimeter. Okay, this is very compact size. And what do you think about the frequency band? Because if you have very small size of the antenna, then your frequency will be at high frequency. Okay, like at 28 gigahertz, but I designed this antenna at 5.8 gigahertz frequency band. Okay, even this is resonating in free space. Okay, in 5.8 gigahertz, and this is wide band. Okay, and you can see axial ratio is less than 3 dB. Okay, less than 3 dB, and it is at 5.8 gigahertz almost. Okay, and this antenna is flexible because I've used polymer substrate. And you can see you can do simulation in the CST like this. Okay, you have done simulation for the x-axis and x-axis, and then the along y-axis. Okay, and you can add graphs in the paper. Okay. I do not do much simulation in my laptop. I use my PC to in my university for quick simulations, but here it is taking much time. Try to make a good shape of the design, okay, or so that if it is good, then we can also save that design for future publications. You can also, even if you want to design a new antenna, you can also pick one paper, like you have this paper. You can also modify the shape of this design, okay. And you suppose you can, what you can do, like you can add another patch, okay. Let me take a snap and explain in PowerPoint. Like you have this design, okay. Some researchers do in this way that okay, suppose you this antenna behaves a dual band, okay. You can make it multi band, you can make it quad band, okay, like this. You can add another patch, okay, like this, okay. Connect this patch like this, okay, and create another pole, okay, like this, okay. And also here like this, okay. Then it maybe it will work at multi-band, and okay. So in this way you can do it, or also you can modify the ground plane, okay, like you, as I have done in the paper, okay, like this. Okay, you can modify the ground plane, or you can add slots, okay, if to if there is a chain with slots, okay. As I told you before, in antenna designing you are free to do anything, okay. You can add slots like this, okay, to check whether if it has impact on the resonant frequency, okay. Okay, now you can see with the patch behind this one, okay, it is working very you can see now it is also dual band.
See, so show us the voltage standing with brush.
Yes, you can see this is below 2, okay, less than 2. It should be less than 2 or approaches to 0, okay. For ideal antennas it is approaches to 0, but it should be less than 2. Okay, now I want to show you how to create a graph for the gain versus frequency graph, okay, because here you are not able to find the graph of the like this graph is the efficiency, this is the efficiency. You can directly export the this one, okay. This is the efficiency and this is your frequency, so this is your efficiency versus frequency graph. But for the gain you are not able to see here, okay. So you need to go to the some people do in the field monitor, but like a broadband here, okay, leave it. Just go to the post processing, go to the result template, okay. Then you need to calculate the far field antenna properties. Let me check far field result. Okay, yes, did you understand? First you need to go to the far field and antenna properties, then you need to go to the far field result, because these results lie in the far field. Okay, so that's why you need to choose the far field result. Okay, then you can see here maximum gain versus over frequency, and also you have many other options like power radiated over frequency, and also directivity, also angular 3 dB width. Okay, many other front to back ratio. Okay, and maximum over gain over frequency. Okay, then click on it and go to the all setting. Okay, then here you will find many options, and you need to select which one you want to calculate. I want to calculate realized gain. Okay, and if your antenna is circularly polarized, then you can click on the XZ ratio. If it is linearly polarized, then no need. Okay, then click on the broadband. Okay, broadband means if you click the single band frequency, then it will only calculate at the one frequency, but if you need the samples or add all the frequency band, then you can click the broadband. Okay, and then you need to just this one. Okay, now click OK. Okay, now click on the you will find option here. Okay, then click on the evaluate. It is possible only after the simulation. Okay, first simulation. Okay, so this is your you will find here in these tables. Okay, in this one. Okay, so you can see this is your realized gain versus frequency graph. Okay, so you can export this one. Okay, like this, and to draw in other softwares. Okay, even you can copy this one and paste in here. Okay, in a new folder. Okay, if you want. So in this way you can get the realized gain, or you can get the IEEE gain, or you can get the directivity versus frequency graph. Okay, okay, so do you understand the task you have for the next day? I need to end up this session because I have a class now in my university. I need to go to the university, and uh, for this task you need to show me your screen, your designs. Okay, using this as I am showing you. Okay, and you need to use these things. Okay, and to show me these things. Okay, so do you understand how to design the things? It is very easy task, not a complex one. Okay, so be ready for tomorrow, and I hope inshallah everything will be fine with us, and we will not have any problem. Okay, how to calculate SCR? Dear brother, we are not simulating the antenna on human body. Okay, but you can find here option. Okay, because we did not for okay, I show you. You need to go to the field monitor. Okay, go to the click on this one. Okay, power loss density and also SAR. You need to simulate this one. Okay, after simulation this option will be enabled for you. Okay, and but you can see there is no human body behind this antenna, so that's why you cannot be able to calculate the SAR. Okay, once we will study the human body or implantable antennas, then we will learn how to calculate this SAR. Okay, I need to use my university computer because in this laptop it is not able to calculate SAR values. Okay, then see you tomorrow. Okay, I have a class. I need to go because it's already very late. I have only 10 minutes to go to the university. Okay, so see you tomorrow. What is your question? The modification of the design is based on the surface current. Yes, yes, you can. If you see the difference in the surface current and you can see the red portion, then it's up to you. Okay, I just want to see how you will design antenna and how you operate at 2.45 gigahertz. Okay.